So here we have a typical container. Comprising two immiscible liquids. This is the free surface. This is liquid of density rho, and this is liquid of density 2 rho. Alright. So, with this combination, there is fluid jutting out of this, and the streamline now follows a path. Very clearly, there is volume flow rate, which is V into A here. V is the velocity of a flux, and which remains the same. Now, very clearly then, if the velocity increases, the area of cross section must decrease. Area of cross section must decrease. So all that we need to do is we need to apply Bernoulli's theorem. We need to apply Bernoulli's theorem. What I'll do is, let's say, just inside, just here, and just here. Let's say by the time it reaches this point, say V1 is the velocity on reaching the ground. So the P by rho g, etc. at this mouth, that means just before entering the tube, pressure realized at this point, the pressure here is P atmospheric plus rho gh plus 2 rho g into h by 2, right? That's the pressure just inside. So by 2 rho g, the density here is 2 rho. Now the area of cross section here is much larger compared to that at the exit, so the velocity here can be neglected for practical calculations, right? The velocity, the dynamic head v squared by 2g could be neglected here because the area of cross section is large, right? If I look at this as the datum, that is z equal to 0, I could look upon this as the datum, z equal to 0, v is 0 and z is 0 at this point, right? That must be equal to at the exit. At the exit, the pressure is P atmospheric by 2 rho g. The dynamic head is v squared by 2g. The dynamic head is v squared by 2g. The datum is 0 once again here. Now, on arrival at the bottom, the pressure here is P atmospheric, right? The pressure here is P atmospheric by 2 rho g plus V1 squared by 2g plus, what's the datum here? Minus h by 2, because if this is z equal to 0, this would be positive datum, this would be negative datum. So this would be z equal to minus h by 2. Yes or no? So now this would enable this, and this would give you v squared, right? So what do I get for v squared by 2g? V squared by 2g, if I use this and this, is rho gh plus rho gh, so it will be simply h. So v then turns out to be root 2 gh. At the exit, v turns out to be root 2 gh, and if I use this, once I have got v equal to root 2 gh, this would become simply h, this would simply become h. So then v1 squared by 2g is h plus h by 2, that is 3 squared by, that is 3h by 2. Yes or no? If I use these two, plugging in v equal to root 2gh, this will become h plus h by 2, 3h by 2, v1 squared by 2g is 3h by 2, or v1 is root 3gh. That's v1, the velocity on reaching the ground. So all that you need to do is apply continuity equation. Continuity equation would guarantee v into a is the area of cross section here, and it thins down to, let's say, a prime here, and acquires a velocity v1, equating the volume flow rate at the exit and on reaching the ground. A you know, and a prime could be obtained given the knowledge of v and v1. Got me? The initial depth, the initial height above the orifice is given to be 0.81 meters, right? Now, greater the depth here, the greater is the velocity of a flux, right? And for the same descent, it would have a greater range, right? For the same vertical fall, which will take the same time irrespective, right? Which will take the same time irrespective of the velocity of a flux. The time taken to dip by 1 meter is going to be the same irrespective of the velocity of a flux. So now, higher the velocity of a flux, greater would be the range, right? As the water level dips, the velocity of a flux root 2gh will dip, right? The range will go on decreasing, range will go on decreasing. So now, for a certain height h, say x, for a certain height x, the range is at its threshold. The range is at its threshold. This whole thing, x was originally 0.81 meters, but it dips to x, right? X is the threshold value of the depth for which it's just able to reach the wall. Now, if it dips lesser than this, then the velocity of efflux will reduce and the range is bound to decrease and it cannot cross the wall. So, x is that, the required threshold depth, So, let's find out this threshold depth for which it's just able to reach the wall. Any shortfall from x will prevent it from reaching the wall, right? Okay. So, very clearly, let's say it takes t seconds for a vertical descent of 1 meter. So, 1 is half gt squared, and the velocity here of a flux is such that v squared is 2gx, right? For a vertical descent of 1 meter takes t seconds. So, 1 is half gt squared, initial vertical velocity is 0, and the range of 1 meter, in order that it could just reach the wall, range has to be 1 meter. 1 meter must be v into t, right? So, this one I can write as half g into t squared, which is 1 by v squared. So, I get, if I use 1 and 2 by eliminating t, v squared is g by 2, but v squared is 2gx. So, x then becomes 0.25 meters. X then becomes 0.25 meters. That means when it goes down from 0.81 to 0.25 meters, the range goes from a higher value to just about reaching the wall. When the depth falls lesser than 0.25 meters, it cannot cross the wall. That's what happens here, right? So now, we will have to find the time it takes for the depth to go from 0.81 meters to 0.25 meters. That's the time that we want to find. So what we do here is, so now I can forget all about this. Now this x is not threshold, this is now a variable. This is now just a variable, right? So we want to find the time it takes for the depth x to go from 0.81 to 0.25 meters. Treating now this x as a variable. At this instant of time, the rate at which water is flowing out of the tank is a into velocity v root 2gx, right? Now, if capital A is the area of cross section of this, then the rate at which the volume here is increasing, the rate at which volume is decreasing here is magnitude of A into dx dt. Rate of fall of height into area of cross section is the rate at which the volume is decreasing, and that must be the rate at which volume is escaping, right? So this must be equal to this. Hey, but x is decreasing with time, so dx dt is negative. So if I have to strip the modulus, I'll have to plug in a minus sign. Give me a minus, right? Which means I get a root 2g into dt by capital A is x to power minus half dx, and then all that you need to do is to integrate both sides, right? At time t equal to 0, x was 0.81 meters, right? We need to find the time t in which x becomes easy to integrate, because this will become x power half by half, and x power half will 0.5 minus 0.9. So perfectly managed situations. And again, g is 10 and a is root 5. So again, this will be 2. This will be 2. When I divide this by this, I'll get 2. And then this a is 4 into 10 to the power minus 4. So simple calculations here, right? So you can calculate the time it takes. So beyond this t seconds, water will not cross the wall. The jet will not cross the wall. That's what would happen, right? Look, when the container is imparted a rightward acceleration, the water level will acquire an inclination. The water level will acquire an inclination with the horizontal theta such that tan theta would be a by g. Tan theta is going to be a by g. Now, in a limiting situation then, when things have spilled over, is going to have this just about reaching the highest point. It can't go higher than this for a complete spillover, right? So then it goes down to this level. A is 8 meters per second squared. 8 meters per second squared. Tan theta is 8 by 10. 0.8 is tan theta, right? So this is 2 meters. This is 2 meters. So this length is going to be 1.6 meters. This length is going to be 1.6 meters, and this is going to be 0.4 meters. Right? This will also be 0.4 meters. Which is below C, which obviously is below C because C is 0.5 meters above the ground. Now, this is the water in the container. Realize that this height, average height here is 2 plus 0.4 by 2. 1.2 meters is the average height here. Is the average height here into area of cross section, which is 4 square meters. 4 square meters. So the final volume here is going to be area of cross section, which is 4 square meters into average height 2 plus 0.4 by 2. These many cubic meters, 1.2, so 4.8 cubic meters is the final volume left in the tank. 4.8 cubic meters is the final volume left in the tank, and the initial volume, as you can see, is 4 square meters into 1.5, right? 1.5, so cubic meters, so 6 cubic meters. So the volume that has spilled over is the change in volume, which is 1.2 cubic meters or 1200 liters. That's the volume that has spilled over from the tank. There is a cylindrical wooden floor whose base area is S and whose height is capital H. Drips on the surface of water. Density of wood is D and density of water is rho. What must be the work performed to take the float out of water? What must be the work performed to take the float out of water? Now, for sure, when it's floating in water, there is part of it which is submerged in water. Let's say small h is the portion which is submerged in water, and from laws of flotation, weight of the body is weight of fluid displaced. So h into rho would be proportional to the weight of the fluid displaced. That must be equal to capital H into D, which is proportional to the weight of the wooden float, right? S etc. gets cancelled. I've cancelled. This is laws of flotation. Now, so this is the initial state of the wooden float. And there is part of it which is jutting out, which is H minus small h. H minus small h is jutting out. In a situation of this kind, the forces acting on it are, there is weight which is acting downward, mg, and there is upthrust which is acting like and they balance each other. What I want to do is, when I raise it, and I'm talking of the minimum work done, that means I'm raising it in a manner that I'm not adding kinetic energy to the system. If I'm not adding kinetic energy, it implies that at all points of time, the external force applied must be equal in magnitude and oppositely directed to all other forces acting on it, right? So that the movement of this is quasi-static and no kinetic energy builds onto the wooden block, right? So at all points of time, that force must balance the force because of gravity and force because of the new upthrust at that point of time, right? Now, at some instant, let's say, and by the way, this mg will not change with time, but the upthrust will decrease. Why? Because lesser amount of volume is submerged, so the upthrust is going to be lesser, right? So the external force applied upward, what will happen to that? It has to, because downward force remains the same, the upward force decreases. So the support to the upthrust, support to the external force will decrease. So you will have to apply greater and greater external force so as to counter mg minus the upthrust. So at some point, let's say this is an intermediate state where x units are already jutting out of water. There is h minus x below water. The forces acting are mg like this, downwards, and then there is upthrust, which is weight of the fluid displaced, which is going to be s into h minus x to rho into g. That's the upward force, right? Yes or no? And there is this external force at this instant of time, which will be a function of x. So this external force, intermediate external force, is what? mg minus the upthrust. So minus s into h minus x into rho g. Now for a small displacement in the upward direction dx, this F external will remain practically the same. So then the work done is going to be, for a small displacement upwards, mg minus s into h minus x into rho g into dx, the total amount of work you're seeking by the external force. This would be the minimum amount of work, where x changes from capital H minus h to capital H. X changes from initially capital H minus h to finally the entire height capital H, right? So x changes from h minus small h to capital H. Yes or no? Now easy to integrate. So this work external is going to be mg into h minus s rho g, h minus x whole squared by 2 with a minus sign. This will make it plus h minus h capital H, right? Initial mass, total mass of the wooden block is going to be S into capital H the volume, capital H the volume into density D into G, and this H can be replaced by capital H into D by rho, capital H into D by rho. Rho is this, right? And then you have S rho G by 2 when x is h minus h, so this will become h squared, will be h squared, and when x is capital H, it will become 0, and this h squared I can replace by hd whole squared by rho squared, hd whole squared by rho squared. H into small d, all of this small d, small d, d is the density. So this is what it would. Okay, so we have an arrangement here in which there is a uniform cross section through which a fluid of density rho flows past with a velocity v. We will not change the time owing to continuity considerations, because v into area of cross section has to be maintained, and since the area of cross section is not varying, v will be maintained constant. So now at the two limbs, opening of two limbs, realize that for the fluid that is flowing, the velocity remains the same. Right? But the datum is increasing. So the pressure will decrease. As you go from here to here, the fluid pressure will decrease, which means if the fluid pressure here is more than the fluid pressure there, so that higher fluid pressure will depress it more compared to this limb. So there would be a difference in heights of mercury levels in the two limbs, right, owing to the difference in fluid pressure, right? In any case, say if this was P2 and this was P1, this was P2 and this was P1, then between these 2 points I could apply Bernoulli's theorem. So P2 by rho g plus P squared by 2g will get cancelled from both sides. Don't care about that, right? That must be equal to P1 by rho g plus, now the z here, this angle is theta, this is d, so the z here is going to be d tan theta, it's going to be d tan theta. If the z here is 0, the z here is going to be d tan theta. Right? And so this gives me like a P2 minus P1 is rho g into d tan theta. Now, equating pressures at these 2 points along this dotted line, along dotted line, if I equate the pressure because of this and the pressure because of this, then at this point I have very clearly P2 plus rho G by 2, right? That must be, now the pressure here, because of this Y1 units of fluid, it's going to be P1 plus rho G Y1 plus rho mercury G into delta H. And from this, I can obtain my P2 minus P1. See? But the P2 minus P1 that I obtained from this is actually rho G d tan theta. Plus rho G into Y2 minus Y1 is rho mercury G into delta H. Equating the P2 minus P1 obtained from the two equations, this is what I get, and the delta H, okay, difference in mercury levels could be obtained straight out of it. Right? So in this arrangement, the U tube is accelerating to the right with an acceleration A. And on two sides, you have different fluid. On one side, you have fluid with density 2 rho. On the other side, you have fluid with density rho. And you want to be able to find the height, given that both the levels are the same. Both the levels are the same. First of all, by mere inspection, can you suggest which one would be 2 rho and which one would be rho? Left one would be 2 rho. Left one would be 2 rho and right one would be rho. Why? Now, okay, fine. That's an acceptable explanation. But very simply speaking, look, if I look at the volume AB, the volume of the fluid, which is a mixed volume, AB. Just look at the free body diagram of this volume AB. It is two fluids, one with some density, the other one with some other density. And now if I had to draw the free body diagram of this, then at the cross section at A, there would be pressure P1. At the cross section at B, because of this fluid, there would be pressure P2, right? And if the whole thing is accelerating to the right with an acceleration A, then obviously the pressure here must be larger than the pressure there. And for the same height, if the pressure here is larger than the pressure there, then the density here must be larger than the density there, right? And therefore this must be 2 rho and this must be, right? So now all that I need to do is, I need to apply Newton's second law to this column, horizontal column. I need to apply Newton's second law to this horizontal column. So when I do that, the pressure P1 would be 2 rho GH minus the pressure P2, which would be rho GH into the area of cross section, let's say S. S is the area of cross section. So that's the net force acting to the right on this column. That must be mass of this plus mass of this into small a. Mass of this plus mass of this into small a. Mass of this is going to be 2 rho G into L by 2 plus mass of this rho G into L by 2 into S, the area of cross section, into the acceleration small a, right? So this readily gets, S will get cancelled and you will have H available in this equation. Alright. So we have a frustum of a cone kind of a structure here of length L and area of cross section linearly increasing from A to 2A. And it's also given that the pressures of the two cross sections are maintained the same. Now, in the very first place, this area of cross section has doubled. Means the velocity must have become to maintain the same volume. The velocity at this cross section is V naught. The velocity here must have been 2V naught. The velocity here must have been 2V naught to maintain the same volume flow rate. Continuity equation, V into A must be constant. And then between at this cross section and this cross section, I can equate P by rho G plus V squared by 2G plus V. P is the same, so the pressure head is the same. So V squared by 2G for this cross section is 2V naught squared by 2G. If I take this as V equal to 0, if I take this as V equal to 0, then the dynamic head here is going to be V naught squared by 2G plus the datum here is going to be L sine theta. Do you realize that? L sine theta, Z is going to be L sine theta here. This is L. So this is going to be L sine theta. And then we clearly have 3V naught squared by 2G L sine theta, where V naught squared is GL by 2, V naught squared is GL by 3 by 4 is what it will become. So sine theta would be 3 by 4. Theta would be sine inverse 3 by 4 there. Such would be the angle of inclination. Alright. We have a situation here where there is this tank filled with water to depth H, and there is an orifice right at the bottom with area of cross section small a. One of the things for sure is that the velocity of a flux here is going to be root 2 GH at this point of time. Right? V equal to root 2 GH. The velocity here would be less, approximately 0, but still it's going to have some value. So now to be able to find the velocity here, V1, velocity in bigger area of cross section, we must have V1 into A is V into small a. So the V1 is known at the top cross section is A by capital A into root 2 GH. Very clearly, as H is decreasing, V1 is decreasing. So the top surface has a retardation. The velocity of the top surface is decreasing, therefore the top surface has retardation, right? If I look at V1 squared from here, then A squared by A squared into 2GH. That's V1 squared. If I differentiate both sides with respect to H, I get 2V1 dV1 dH equals A squared by A squared into 2G. So V1 dV1 dH, don't you think this is a measure of the retardation? A squared G by A squared V dV dH, that will measure the retardation. So the retardation would be of magnitude A squared G by A squared, A squared G by A squared into the retardation, right? So we have a reservoir of water and we want to model it around X so that the range X is the greatest, right? One thing, given H, V is going to be root 2GH, right? Now the height through which it falls is 4 minus H. 4 minus H is the height through which it falls. So the time it takes to reach the point A, the time taken to reach the point A is going to be root 2 times the height through which it falls, which is 4 minus H by G. Root 2 times H by G, root 2 H by G is the time it takes to descend, 0 initial vertical velocity, and the X, the range covered with a constant horizontal velocity VA, that is X, is going to be root 2 GH into root 2 into 4 minus H by G. That's going to be X. Now this is 2 root h to 4 minus 8. The graph of x versus x here is when h is 0 and h is 4, it becomes 0. It goes like this. These are the two roots. And at h equal to 2, it becomes a maximum. H equal to 2 becomes a maximum. Hey, but you don't have h equal to 2 available. You don't have h equal to 2 available. Ideally, you would have, if this was 4 meters in depth, then at h equal to 2, it's going to be a maximum. But there is only 1 meter available, which means h can go only up to 1 meter here. So the maximum would be at h equal to 1 meter. The maximum x would be at h equal to 1 meter. Right? If the h was greater than 2, if the h available was greater than 2, then the maximum would have been at 2. But since it's less than 2, the maximum available is at h equal to 1 meter. H equal to 1 meter. Got it? Now obviously, with the core being in this position, say this gets inclined at an angle theta, the free surface such that tan theta is going to be a by g. That tan theta is going to be a by g. Clear? Forces acting on the core. Now we look at things in the container frame of reference because I need the relative acceleration. So I look at things from the container's perspective, right? The container is an accelerated frame of reference, right? There is like a mg cos theta acting this way. There is normal force and acting this way. There is mg sin theta acting parallel to the incline, right? Now on top of it, I need to have, if I look at the container frame of reference, then what would this be? Pseudo force Ma in this direction. Minus Ma naught means Ma leftward. That's a pseudo force. That's a pseudo force. And this angle is theta. This angle is theta. Clear? Now, in this direction, the n would be such that it will balance all other forces. So, no relative acceleration in this direction. So, let me look at the prospect of having a relative acceleration parallel to the inclined. Parallel to the inclined, m a rel, relative acceleration, that must be mg sin theta minus ma cos theta. That must be the relative acceleration parallel to the inclined, mg sin theta minus ma cos theta, right? So, this would be m into g sin theta minus a cos theta. Hey, but g sin theta is actually a cos theta. G sin theta is a cos theta. This is, so relative acceleration is just before the duct, the gauge pressure, let's say, is P prime, which is 0, and just before this, the velocity V prime is also 0, right? And all of this is at the same datum, so we will not bother about the datum, right? After all, if you look at the energy change that takes place from here to there, then that must be the energy provided by the blower. So energy just before entering the inlet duct, E1 is 0 because P prime by rho g V prime squared by 2g plus z, that's 0, right? Because P is 0, V is 0, so E1 is 0. The energy here, E2, is going to be P epsilon by rho g plus, now V2 is known. Why? Because Q dot, the volume flow rate, is going to be the area of cross section here, pi d2 squared by 4 into V2. So V2 is actually known to us from the volume flow rate. Volume flow rate is the same through the entire cross section. That's continuity consideration. So Q dot is going to be area of cross section into the velocity V2. So V2 can be obtained from this equation, from continuity equation. So the energy E2 is V2 squared by 2G and Z is 0. So how much of energy in meters or joules per unit weight provided by the blower? E2 minus E1 is the energy in joules per unit weight of the fluid into rho Q dot into G. These many newtons per second. So this would give you the watt output of the blower. This would give you the watt output of the blower, and this divided by eta would give you the output of the motor. This will give you the specification of the motor. These many watts will give you the specification of the motor, right? Right. Part of the problem. Now we want to find the gauge pressure at the inlet. That means just after all, you know, the atmosphere, and this is just inside the duct. So the pressure here has to be less than the atmospheric pressure for it to flow in. Otherwise, how would the flow occur? That means you are creating a suction region here, a low pressure region here, pressure lower than the atmosphere, so that it could suck air in. Okay. So the pressure, gauge pressure here is going to be negative below atmosphere, right? Gauge pressure here is going to be negative, and we want to find the gauge pressure at the intake. Just before the intake, it's 0. Gauge pressure is 0. At the intake, I want to find the gauge pressure. So at the intake, the velocity developed is V1. Therefore, V1 can be found from Q dot equal to pi d1 squared by 4 into V1. That's Q dot. So V1 can be found, right? And just before and just after, I can equate the meters because there is no source of energy. It's just that from 0 gauge pressure it becomes negative gauge pressure. So gauge pressure decreases. So the velocity increases to maintain P by rho g plus V squared by 2G constant, right? That's what happens. So if the pressure at the intake is Pi, then Pi by rho g plus V1 squared by 2G, that must be equal to the total meters here, which is 0 in gauge pressure. So the gauge pressure here, which obviously turns out to be negative, is minus V1 squared into rho by 2, rho by 2, right? So you can find the inlet pressure just after entering. Just before entering, it's atmosphere, and it's a region of low pressure here, suction region. So pressure would be lower than atmospheric, so that it could actually induct air in, right? That's what happens. Okay? Specific weight means gamma of air means rho of air into G. That's what it means. Specific weight means rho air into G, right? I mean, this will give you kilograms per cubic meter into G will give you newtons per cubic meter, right? Let's say rho of water is rho W. Now, see, when there is flow through this duct, why should the water rise here? Between this point, that is the atmosphere from where where air is drawn in, right? Build up of velocity here, then the pressure here must be less than the atmospheric pressure. The pressure here must be less than the atmospheric pressure. That means the pressure here is negative. The pressure here is negative. Now, the pressure here must be 0. The gauge pressure, I am talking of the gauge pressure, must be 0. So then the negative pressure plus rho GH, that must be 0. That must be 0. Or let's say, if P naught is the atmospheric pressure, let's say talk in terms of absolute pressures, right? And P1 is the pressure here. P1 is the pressure here. Well, I know the velocity here because Q is going to be pi d1 squared by 4 into the velocity. So I know the velocity in this stuff. I know the velocity in this, right? So then between this point and this point, if I apply Bernoulli's theorem, then P1 by rho g plus V squared by 2g, g is the same. That must be P naught by rho g. And this is still air which is being cold air, right? Low pressure region created in this stuff. Should be this. Yes or no? Where this rho is rho of air. Rho of air. Rho is rho of air. Right? Now, the pressure here plus rho GH, that must be P atmospheric. See, what's the pressure here at this level? P1 plus rho GH, P1 plus rho GH, and that must be P atmospheric, which is P naught, right? So P naught actually is, if I apply pressures here, P1 plus rho GH, rho means now rho of the liquid, rho of water, GH. So all that you need to do is take P naught minus P1 here, P1 minus P naught minus P1 turns out to be V squared by 2G into rho G, rho of air into G, that must be rho WGH. Right? And rho A into G would be gamma of air. Rho A into G would be gamma of air, rho water into G will give you H. Clear? Saline arrangement. Now there is a small duct. The objective of this, if this is filled in by air, what really transpires is that this becomes a region of atmospheric pressure. That means at P the pressure is atmospheric. At P the pressure is atmospheric. At A therefore, that means H2 units above B, the pressure is going to be P naught atmospheric pressure minus rho G H2. So H2 units above B, that is the pressure at A, is going to be atmospheric pressure P naught minus rho G H, minus rho G H2. At the exit here E, the pressure is atmospheric and the velocity is between A and E. I can apply Bernoulli's theorem. Again, this area of cross section is much larger compared to this, so the velocity here can be neglected. The dynamic head here is practically 0. So pressure at A, which is like P naught minus rho G H2, P by rho G, V is 0, Z is H here, right? That must be pressure here, which is P naught by rho G plus V squared by V squared then becomes H minus H2 into 2G. V is root 2G into H minus H2. That's the velocity with which the flow occurs. So in this standard arrangement, there is liquid flowing through this with a certain velocity, call it V naught. V naught is the velocity through it with which it's flowing. Now, right above this, let's say the pressure is P1. Just above this limb, the pressure is P1. And the velocity obviously would be V naught. Now, when a sample is inducted in, it strikes this wall and it comes to rest. So the flow has 0 velocity here. Same datum though, because this is not a thick pipe, a thin pipe, so the same Z. So the dynamic head becomes 0, the pressure here becomes larger than the pressure here. So the pressure here is, let's say, P2, which would be larger than the pressure here, which would be P1, accounting for the difference in heights in the two limbs, right? So between these 2 points, if I apply Bernoulli's theorem, then P1 by rho naught G plus V naught squared by 2G, G is the same, that must be dynamic head 0 here, right, is P2 by rho G plus 0, right, and evidently P2 minus P1 is rho of the liquid G into delta H, yes or no? So this P2 minus P1 from this equation could be written as rho Lg delta H, and the V naught could be obtained from this equation. Once V naught is obtained, the volume flow rate is going to be S into V naught, is going to be the cubic meters per second flowing through the duct, right? This is a practical arrangement. They actually do it this way. To find the volume flow rate, this is what they do. They connect a U-tube like this with a small horizontal portion sticking out, causing the dynamic head to be 0 and the pressure to build up here, and they can witness the change in height delta H. Based on delta H, they can model the velocity flowing through this duct and therefore the volume flow rate flowing through the duct. That's what they do in real life. I mean, in combustion arrangements, you know, when they want to find the volume flow rate through a pipe, this is what they do. They connect a U-tube like this and they measure this delta H, and from there they can readily compute the volume flow rate through the duct, right? Basic idea here. There is flow occurring through these channels, and you want at C this fluid to come all the way through height H and join the mainstream of it. That's what you want. Evidently, the pressure here has to be low so that it could suck in. How much lower? That's the point. One thing, in order, that means the pressure at C so that it could just rise to H. Let's see what's the pressure at C so that it could just rise by an amount H. The pressure at C so that it could just rise by an amount is like Pc plus rho of this liquid. Is it the same liquid? The same liquid, perhaps. Same liquid. So Pc plus rho Gh. That's the pressure. It could be pressure atmospheric, P naught. So if the pressure at C just becomes equal to Pc, then this would just about rise to a height H, right? But if the pressure at C is less than that Pc, not only will it rise to a height H, it will rise with a velocity and it will join the movement, right? So essentially, the pressure at C has to be less than this Pc. Do you realize that? This is the Pc that will just cause water to rise to the height H. That will just cause water to rise to a height H. You know what I am saying, right? That means the actual pressure at C could be less than Pc, that is Pc equal to P naught minus rho Gh. I mean, lower the pressure at C, the merrier it gets in terms of raising it to this height and causing it to join the mainstream of flow, right? Isn't it? Huh? So now let's say the actual pressure at C is P prime C. So P prime C has to be less than Pc. That's the idea. P prime C has to be less than Pc, isn't it? That's the suction pressure. The lower the better. right? So now let's say if the actual pressure at C is P prime C. One of the things that you would easily appreciate is if I apply Bernoulli between this atmosphere and this atmosphere falling through a height h, then the velocity with which this flows is v squared equal to 2g capital H, right? So v is known. If AC is the area of cross section here, if AC is the area of cross section here, and A is the area of cross section there, A is the area of cross section here, then very clearly A into the velocity here, that would be the volume flow rate, the topmost level, A into V, that must be equal to AC into VC, that must be equal to AC into C. Or let's say this is A, this is perhaps A1, A1. So that's A1, A1, and this must be equal to, and let me call it V1, let me therefore call it V1, that must be A into V, each is equal to the volume flow rate. Continuity equation, right? Now between this and C, I can apply Bernoulli's theorem. P here is P atmospheric, P naught by rho g, P naught by rho g, plus this I can neglect, right? V1 is 0 because this is very narrow cross section compared to this, so V1 is much smaller than Vc. So if I neglect that, the Z for this compared to C is Hc, right? The pressure here is P prime C, plus the velocity is Vc squared by 2g, that's the dynamic head, 2g, and the datum here is 0 because I have taken this as a, right? So from this I realized that I could replace the Vc squared by a square V squared by AC squared. This Vc squared can be written as a square V squared by AC squared, yes or no? So this Vc squared I write as a squared V squared by AC square, right? Where this V squared is actually 2g into capital H. This V squared is 2g into capital H. A squared 2g into capital H by AC squared, yes or no? Now this Pc then turns out to be, this P prime C then turns out to be P naught by rho g plus Hc minus A by AC whole squared into capital H. That's P prime C. That's P prime C. When I solve for P prime C, this is what I get, P naught by rho g plus Hc minus A squared by AC squared into capital H. But this P prime C has to be less than Pc. So it has to be less than P naught minus rho gh, P naught minus rho gh, yes or no? No, I'm sorry, this by rho g, this by rho g, this P prime C by rho g is this, and this has to be less than P naught by rho g minus h, then P naught by rho g will get cancelled, and we have A by AC whole squared greater than H plus Hc, and H plus Hc by capital H, square root of that, A by AC whole square, the limit can be found straight away, right?